Here's another function example. h of x equals 8x squared minus x cubed plus 7. This starts with an x squared, but it's actually a cubic because of the middle term. So we'll look at graphing that in Desmos, and then k of x equals negative 8x plus 26. Once again, what we want to do is look at when those functions are equal. We want to look at when the h function is less than or equal to the k function and when h is greater than the k function. So different things to look at. Let's first graph them in Desmos. So our h function, h of x, equals 8x squared minus x cubed plus 7. So you can see little bits and pieces of the graph, but not it completely. So let's graph the other one and then we'll adjust the window. K of x is equal to negative 8x plus 26. And that one, again, you don't see a whole lot of. But one thing to kind of be aware of is that this is a line. The second function is a line, and it has an intercept of 26. So we're not graphed nearly high enough to see everything on this for these functions. So let's expand using graph settings. Why I want to use graph settings is that with polynomials, especially when you have a cube or a higher power like a cube or a fourth power as we see in h, what we want to do is have an elongated y-axis. So instead of just going from negative 10 to 10, why don't we go from negative 100 to 100 as a starting point? So, and then on the x-axis, we can kind of keep it as it is or adjust if we need to. But you see how we can see that cubic graph showing up like we saw in the other example, and the line more clearly because we've expanded the y-axis quite a bit to take into account those exponents. Those higher exponents are going to stretch the graph quite a bit on the y-axis. So here we have a pretty good representation of the two graphs and where they cross. We can use Desmos to look at those intersection points. And I'll copy this graph over into our handout so that we can see what's going on while we look at what we're trying to solve. So here we are back on the page with the questions, and we have a picture of our graph here. So let's start with where solving the statement where we have the functions equal. So if the functions are equal, what we want to look for is their intersections, and we can actually see them here, here, and here. In particular, I've underlined the x values because our answers should be related to the x values of those intersections. So I mentioned above to round off to the nearest, I think, second decimal place. So this would be negative 1.85 as the first one on the left. The middle one would be positive 1.18 rather, and then the one on the right would be 8.67. If you check with approximate values, keep in mind that you will have an approximately true statement on the two sides. It should be really, really close, but they won't be exactly the same when you plug in to h and k. You won't get exactly the same thing for each of these values. You'll get really close values, but not exactly the same thing. Now, the next problem down was to solve the inequality where h is less than or equal to k. So we're interested in when the cubic, or the red graph, is less than or below the line. So let's highlight those values. So the red graph is below the line right here, and it's also below the line as we right at the bottom here where we're going out and getting into big x values. So our solution set would be the union of those two regions. The first region where the red graph dips below the line would be from negative 1.85, and keep in mind that because we can be equal, we would want to use a bracket. So negative 1.85 up to where it stops at positive 1.18. So you use brackets there because of the equals involved in the inequality, union, and then the next shaded region starts at an x value of 8.67 going on to infinity. Remember, even though it's going down, you're thinking about what's happening as you go right, and that would be on the x values positive infinity. The last inequality would be when h of x is greater than k. So what we want to do is look for when the cubic graph is above the line, which is blue. So it's above on the left-hand side, and it's also above in this big swath here, kind of in the middle. So let's look at what those values would be. On the left side, when it's going really high, it's actually going out to the left, which with x values would be negative infinity. And then it stops here at the intersection at negative 1.85. And I don't have an equals here, multiplying inequality, so I'll use a parentheses. And then the other region that I want to union in would start at this x value of 1.18 and would go until we get to this third intersection at 8.67. Again, using parentheses because we have a strict inequality in this final statement. So there would be our 3 solution sets for these 3 functional statements. Again, you can check any of those by plugging in values and seeing either if with the equation you have the same value on both sides, or with the inequalities whether you have the left side smaller than the right side or the left side bigger than the right side.